Hello class, this is going over major quiz 3, the practice test, so hopefully that you will be ready to take it tomorrow. So I know some of you just watch it. Make sure you listen. I'm going to say and explain a lot more than I'm going to write. And then remember that your practice test is due tomorrow. So number 1, always make sure you read all problems carefully, and if you don't understand them, I highly recommend drawing a picture. So under what conditions do we consider A, acceleration, to be equal to G, gravity, i.e. negative 10 meters per second squared? Which axis are we working with when using AG? Which direction is that acceleration, and does it ever change? So basically the question is asking, when is acceleration equal to gravity? And hopefully you know that if you're standing excuse me, on a surface, you're not accelerating. So your acceleration is not equal to gravity. It is only when you are above that surface that your acceleration is going to equal gravity. So the correct answer for this would be when you're in the air. So this doesn't matter even if you are currently jumping up. This is a common misconception. Even if you are going up, the reason you do not continue falling up but instead go back down is due to gravity. So gravity acts on you the entire time you're in the air. All right, what direction is that acceleration? Gravity's acceleration is always straight down towards the Earth, and that never changes. Gravity never goes up. Even if you are going up, gravity always faces down towards the Earth at any point when you're in the air. All right. And then looking at this diagram, we want to know what the x and y components, do they change, why or why not? So let's first identify what is my x component. The x component are the ones acting in the x direction or the x-axis. So this would be your y, and this would be your x. So you can see that all of these lines right here are acting in the x direction, and it says, does it ever change? And you can kind of just look at these and know that no, they do not change. The why or why not? There is no acceleration in the x direction. Gravity only acts up and down, or only acts down in the y direction. So when something is in the air, there's nothing pushing or pulling it, so there's nothing to cause an acceleration. Therefore, there is no acceleration in the x direction, and that way the velocity will never change. Because remember, acceleration is a change in velocity. All right, what about the y component? Does the y component change? So you can look at the y component. It's this one right here. And in fact, it's absent or equal to 0 right there. And does your y component change? Hopefully you can easily look at that and say, yes, it does. We see it going from very positive to small to 0 to a little bit negative to very negative. And there is acceleration. Acceleration due to gravity. So my acceleration started out positive, and then because gravity kept pushing it down a little bit at a time, and each little bit eventually canceled it out and then made it go negative. So we just kept adding a little bit of acceleration each time. And so when we did that, we increased our velocity until we hit the ground, or we increased our speed in the negative direction until we hit the ground. All right, and then how do the speeds at the different points compare? And I included some drawings for you. Your test will not have these, so you need to be able to think about it. And that's at A, B, and C. And you can see the resultant velocities. hopefully you can tell which ones are larger. But something you should notice, at any point, notice this line is exactly the same as this line. If you pick any line and find its exact spot on the other side, they're going to be the same speed. Different directions, but same speed. It's the idea that what goes up must come down. And since it accelerates constantly the whole time due to gravity, it actually gets the same velocity at all those different points, just in opposite directions. So we'll have the same speed. Remember, it mentions speed. Speed does not have a direction. So hopefully you can say, oh, and also at the top, it loses part of its velocity. It loses all of its y velocity. That is not true everywhere else. So at the top is generally going to be your slowest. So that lets us know that B is going to be the smallest, so that cancels out this one. So remember, if it's on this side, it's very small. If it's on this side, it's very big. B is not a possibility, and actually none of these are. And notice A and C are equal because they're at the same point on your curve. So the answer would be C. All right, and then it asks you to draw the acceleration above. I kind of already did, but I'm going to just make some room here to very clearly write it. So if you want to draw the acceleration in at all those points, remember we mentioned that acceleration doesn't change, so its acceleration at every point would be exactly the same. Because at every point it is accelerating due to gravity, which remains constant. Yes, gravity is constant. Alright, and we were talking about 5 a lot in class. Hopefully this seems familiar. Or actually, nope, this is a slightly different one. So we need to use the other page, so I'm going to pause and erase all of this. Alright, so the velocity of a projectile at launch has a horizontal component, Vx. So all that's saying is that we gave it a name. So it has some horizontal, Vx, and a vertical component, Vy. When the projectile is at the highest point, so right there, when the projectile is at the highest point, write out everything you know about the x and y direction. So x naught, we don't really know anything actually. Xx, we know it's further along, but we don't really know anything. We could probably call this 0 though, where it started. V naught x, we do know. We know it started off at Vx. And remember, we can always assume acceleration in the x direction is 0 of a projectile, and acceleration in the y direction is g, gravity. Your V final is actually the same exact thing because there's no acceleration, so these will not change. Your y direction, we know it starts off at 0. We know it ends at some place higher than 0 because it's the highest point. We know that our initial is this Vy we started with. And at the top, remember, when things are at the top, right here, in the up and down direction, it's not moving. That's that hang time when you see someone jump and they kind of hang, it seems like they hang in the air in that little tip-top point. That's because the velocity up there is 0. So you know at the tip-top point that my acceleration in the x direction is 0, acceleration in the y is g, my velocity is the same it's always been in the x, and my velocity in the y is 0. Alright, 6 might sound like you have to do math. You absolutely don't. So a jet near the surface of the Earth is accelerating vertically upwards at 15 meters per second squared. So it's not accelerating due to gravity because it has an engine. Alright, a piece of the rocket then breaks off mid-flight. Woo. Immediately after the break, the acceleration of the broken piece is most nearly 10 meters per second squared down, 10 meters per second squared up, 0, or 15 meters per second squared up. Well, forget the rest of the problem. Just think, the moment that little broken piece in the air, does it have an engine? Hopefully you know that no, a broken piece does not have a working engine. Is that in the air? Yes. If it's in the air, we talked earlier, what is its acceleration? Hopefully you know, its acceleration must be 10 meters per second down. Because gravity is the only thing acting on it the moment it's let go of the rocket. Sure, is it moving up? Probably very fast? Yes. But it will be slowing down because gravity will act on it and it will eventually fall due to gravity. Alright, 7. In the absence of air resistance, if an object were to fall freely near the surface of the moon, the acceleration would gradually decrease until the object moves with terminal velocity. Terminal velocity is something that only exists with air resistance. It's why skydivers don't get going very fast, because actually there is air resistance. That's why they spread out to slow themselves down a little bit, because the air pushes back up on them. But we just said there's no air resistance, so we don't care about that one. Its acceleration is constant. It will fall with a constant speed. The acceleration is 0. So if the acceleration is 0, it wouldn't fall, and things on the moon do fall. So that's not true. It will fall with constant speed. So constant speed means it's just going to fall at the same rate. Well, think the moon is just a smaller version of Earth, so it has its own gravity. So just like on Earth, the acceleration would be constant. It would just be the gravity of the moon. Alright, I'm going to clear some space, so if you haven't written things down that you wanted to, write them down. Alright, so number 8 is more of just a thought question. So draw a picture of a cannon firing at the wall, considering a significant V, or a large initial velocity. Which will stop the projectile first, the wall or the ground? So it depends how you draw your cannon. Oops. So if you draw your cannon shooting straight, terrible cannon, but that's okay. If you show your cannon shooting straight with a very high velocity, you could probably think, well, even though it's going to go down, it's probably going to hit that wall first. If you thought, oh, hey, my cannon is going to be shooting up, it might miss the wall, it might hit the wall, depending how well your large is. So in general, as long as you consider your wall concrete enough, it will probably, with enough velocity, because this main question is mostly asking how does velocity affect it. So your initial velocity it doesn't necessarily affect the time in the air it takes, as we talked about, but it heavily affects the range, or how far your cannon will go. So since you have a large V0, you can probably assume that it will hit the wall before it hits the ground, because it's going to have a large range. Alright, an object is dropped from a height of h equals 30 meters. Given the equation y equals y naught v naught t, and all this is saying is, this is slightly different notation. I just always say x in the y direction, but these are the same equation. What variable are we solving for? So if I give you all this information, what possible things could we solve for? And actually you could probably solve for a lot, because remember, dropped tells us something. Dropped means that v0 in the y direction, and actually all v0s, including in the x, are equal to 0. If we know height, that tells us our, oops, I realized I just wrote that wrong. Hopefully you caught that. It's not initial. We also know that the initial position in the y is 30 meters. So this is nice because this thing goes away. We know acceleration when something is in the air is always gravity, or negative 10 meters per second squared down. So what could we possibly be solving for? Well, you could solve for one of two things depending on what they ask you. If they ask where does it end up, given a certain amount of time, you could solve for the final position. If it says, oh, it falls and hits the ground, we could say, oh, I know that is going to be 0, and then I could solve for how long it takes to get there. All right, number 10. Draw and consider this. A man is in a long field, and he is not to scale. He's in a long field. So in one hand, he has a ball. The other hand, he has a poorly drawn gun. At the same time he drops the ball, he shoots the gun from the same height. Assume no air resistance and that the gun is parallel to the ground. So he's not shooting up, he's just shooting straight. Will the ball hit the ground at the same time as the bullet? Explain. So this one I'm not going to write out the answers, so I want you to explain in your own words, because this is an important concept I want you to remember. In your own words. So, will the ball hit the ground at the same time as the bullet? Explain. Yes, the ball will hit the ground at the same time as the bullet, because the bullet has a huge velocity in the y direction. Huge. It's a gun. It goes very, very fast. However, excuse me, in the x direction. But remember, what happens in the x direction does not affect what happens in the y. So even though it has a huge acceleration or a huge velocity in the x direction, that doesn't affect where it starts out in the y. Its y is 0, just like the ball, because we didn't shoot it up or down. So its v0 is the same as the ball. If we were to solve this, you could actually just plug it in and it would be like this equation here. All that matters is the height they were dropped at. So remember, if they were dropped at whatever height, then we would find the time, and the times would be exactly the same because they're at the same height. If I had shot the gun up or down at an angle, that would change things, as you probably know. But if I just shoot it straight, they start with the same initial velocity. The only thing acting on them is gravity, and then therefore they would land at the same time. Yes, if there's air resistance, things would be a little different, but really not a lot, especially because you're going at such low heights. The higher the heights, more air resistance, because there's more air they'd have to push through. Alright, so go ahead, think on this, and then write it out in your own words. So pause and finish writing this in your own words. Alright, so final page, almost done. So Steve throws a soda can to his friend from a moving car. If Steve was approaching his friend who was 22.5 meters away, will he catch it or will he be off target? So we want to picture that here's Steve in our car. And also, if he's throwing a soda can, it's a really bad idea. It's just going to be all shook up if it's not already open. In that case, that's gross. So his car is moving 5 meters per second, and he throws his soda can 2.5 meters per second. So notice we have two different components, depending on how you drew it. If you drew it the other way, one would have been the x and one would have been the y, and that's okay. So this is your initial velocity in only the x direction. This is your initial velocity in only the y direction. However, as I'm reading this problem, I'm realizing this is not very good problem because it does not give enough information. For example, it doesn't say if he was 22.5 meters away in this direction to the right, or if he was 22.5 meters in this direction. If he was directly in front of the car, well, he's not going to catch it, he's going to hit him. So this is not a very well worded problem, but you should be able to at least identify how these things can get broken up and what things you might want to For example, if his boy, we don't have a name for his friend, rude. So if his friend was over here, 22.5, and he threw it out of a moving car, well, it would definitely be off target because it has all of this velocity in this direction. So his can would in fact move like this, which would not be very helpful to his friend. It's why if you throw something out of a moving car, you know it's going to go forward some more, because it has this velocity on it as well, because you and the can are moving that way. So even when you throw it, it has both a horizontal and a forward speed at the same time. All right, next question. John throws a book to his friend 15 meters away from him at an angle of 45 degrees with an initial velocity of 1.5 meters per second. How long does the book stay in the air? How high does the book reach if John's release is 0.75 meters from the ground? So, we know, and we're assuming that he makes it, that he throws a book to his friend, who's 15 meters away. Maybe this is Steve and Steve's friend. He's getting back at him for throwing a soda can at him poorly. And he throws it at an angle of 45 degrees. And we know that this is our initial velocity, 1.5 meters per second. All right, hopefully if you're following the step process, remember it's 1, read it, 2, draw a picture, which we have, 3 is then your triangles. So hopefully you're like, oh, I have an angle, we have a triangle here. So its hypotenuse is 1.5, its angle is 45, and we need to find its y side and its x side. So the way we do this is with our sine and cosine. So we know that the y is the opposite, and it's going to be most times, so it's going to be sine theta of our angle, which is 45, I'll put it in later, is equal to the opposite over the hypotenuse. So we can see that this is our opposite, so sine 45 is equal to our velocity initial in the y direction over the hypotenuse, 1.5. Multiply by 1.5 on both sides, we get 1.5 sine 45. And then we know that for this, it's just the cosine version of that. So it'd be 1.5 cosine 45. And then you can plug those into your calculator, make sure you know how. And you get 1.06. If you want to just round that to 1, you could. It makes life easier. And you'll notice they're both the same. And that's because you have a 45-degree angle. Remember, a 45-degree angle perfectly bisects. That means each side is going to be exactly the same, which kind of makes your math easier if you remember it, because you only have to do it once. After this, you need to do your x and y charts. And I'm going to clear this triangle to make some room. So if you need it written down, pause this video. Now we have an x and y chart to fill out. So our x initial, we can just say he starts at 0. We know that can lands at his friend 15 meters away. We know in the y direction, it actually says he starts at 0.75 meters. That's how high John throws it from. Later, we know that v naught in our initial, we just figured out was 1.06. That was our triangle. We're not sure about v final, except wait. The acceleration is 0, so if the velocity doesn't change, my final velocity is exactly the same. Not that this is really terribly important, but just something to think about. We're not sure where it ends up. We do know that our initial velocity is 1.06. We don't know about our final. we know that acceleration in this direction is always negative 10 meters per second squared. So the first question is, how long is the book in the air? So hopefully you can look at this and think, well, which one do I know the most about? That's the one I'm going to use. And we're going to almost always use the first equation. And in this case, x is the one we know the most about, so we can go ahead and use the x. So the first equation, you will have all these equations. X equals x naught plus v naught t plus 1/2 at squared. Notice acceleration is 0, which is very helpful because I can cross this out. So now, and my initial position is 0, so I can cross that out. And then I get 15 equals my original velocity, 1.06 times time. We need to isolate time by dividing on both sides. Remember, we divide because they were originally multiplied. And when we do this, we get about 14 seconds. So hopefully you're thinking, wow, that's a really long amount of time, which it is. So this is how long it would take if it were to reach him. But you might think, well, that's a really long distance, and that's a really low speed. Did it actually reach him? Good question. So, I'm actually going to figure that out next. I know it's not the next question, blah, blah, blah. The next one is how high does the book reach? We'll do that one. But I actually want to know, how far does this book actually go? Because we say it's going to go 15 meters, but does it make it there? So I'm going to clear a lot of this, not my X and Y chart, or my picture, because that stays the same. And let's see. So my X and Y chart is pretty much the same. My only difference is this. I want to know how far it actually goes. So, and that's saying that, let's say his friend catches it at the same height. You know, you don't want to make them reach really far. That's not a good throw. So let's say he threw it really well and it lands in his hand at 0.75 meters tall. So we can use this equation instead to find the time. And actually a lot of times I prefer to find the y, because the y is the one that really determines when it falls. So we can still set up our first equation. You'll notice on these, it's a lot of first equation stuff. When we get to how high, that's going to be a third equation. But, oh, and I broke my own rule. Always write the equation first. So x naught in the y direction, or x final in the y direction is equal to x naught in the y direction plus v naught in the y direction plus 1/2 at squared. Or, if you're thinking, you can think, well, I know at the very top, my velocity in the y direction is 0, and you can use an easier equation because you'll notice this has a t squared, which could make things very difficult for you. I will show both, and you'll see how they both get the same answer. So, looking at this, we know it's 0.75 equals 0.75. Hopefully you can see, hey, might get to cancel something there. V naught t plus 1/2 at squared. I left some variables in for this reason. If I subtract this on both sides, you'll get 0. So you have 0 equals v naught t plus 1/2 at squared. We can factor out one of our t's, so that becomes v naught plus 1/2 a equals 0, which is a lot easier to solve for. And then we plug that in and we get, so we're going to move this to the other side. I'm running out of room here. Equals -5, because half of 10 is t, divided by -5 on both sides. And that thing's only going to stay in the air for 0.102 of a second. So he did not throw it hard enough. And I'm running out of time on my video, so I'm just going to post the answer to how high it is without a full talking through. Alright, so really quickly, this is the work, and then I get 0.81, so he really didn't throw fast enough.